the speaker, the microphone is actually on TV.
Okay,
So here you won't hear.
that's fine.
Um, so yeah, welcome to this month, Big Data Bellevue meetup. My name is Siddharth Agrawal. I'm the organizer of the meetup. My co-organizer is Chaitanya. We've been doing this for about almost 10 years. And we're just kind of keeping track of, how big data has evolved over this time span. And now, as you can see, most things are moved to the cloud, which is great for scalability. Customers need more and more computing power. Gone are the days really of like on-site clusters. And one of the big areas for compute is to do with analytics. So basically capturing your data and then visualizing it, running queries against it. And one of the products that was kind of early in the space is Elastic. I myself had used this product at an earlier startup I was in, and you can really get up to speed really fast because it's uses JSON, doesn't require a schema. It gets you like charting really quickly. So the challenge that we're going to learn about more today is how do you deploy this system on a cloud, not just one cloud, but multiple clouds, so that customers can just use your system and scale automatically. So with that, I'm going to hand it over to Yuvraj, Elastic.
Hey everyone, I just wanted to check those who are on this call on Teams, are you able to hear us?
Well, you can. Yes, able to hear you loud and clear.
Okay, sounds good. Hey everyone, my name is Yuvi. So I'm a product manager at Elastic. So today we will be talking about our journey of how did we build out the Elastic Cloud Serverless product, right? So when we talk about serverless, everyone has a bunch of definitions. We'll try to figure out what our definition was when we built out serverless. So kind of like showing you a quick agenda, like we would spend majority of the time today talking about all the design considerations that we took so that we focus on all the good things and kind of like all the technical things on what were the consideration requirements and where did we have to do a bunch of trade-offs. But before we go over there, we would start with some overview of what Elastic is so that you understand the primitive on how we are trying to build up. So before I go to the next slide, like how many of you have used an Elastic product? Okay, I think everyone in this room. What about people who are on the call? Have you used or heard about Elastic?
Elastic company or Elastic products? What's
Either.
Either.
Yeah.
Oh, okay.
If someone is speaking on the meeting, then they might be on mute. Okay, I will just assume that most of you have. If you haven't, don't worry. We'll talk a little bit about what the product is, right? So so this is an overview of how we started, right? So this is kind of like our journey of 4 products. On the leftmost side, you see kind of like a scale which talks about control, which means that you have the utmost control of whatever the hell you want to do, which means that we give you primitives so that you can shoot yourself in the foot, which means that you have to take more advantage and control of what you're trying to do. And on the right side of the scale is simplicity, where we are trying to give you a simple option for you to get started with. And over in this whole journey, you realize that we started off with the initial product, which was self-managed, which means that you can download the binaries of either Elasticsearch, which is the data store, or Kibana, which is like the data visualization there. So you can bump in any kind of data. You have to manage the whole ecosystem. You have to manage the clusters, you have to manage the deployments, but you have utmost control because you can kind of customize any setting that you want. You can run it in any configuration that you want. If you want, you can do any kind of customization over there, right? Then we realized that customers like the product, but they don't like managing everything, right? So that's where we ended up with taking some simplicity approach and kind of like giving utmost control, but in a controlled manner. That's why we built the product which we call Elastic Cloud on Kubernetes, where we give you the orchestration layer. So now going from managing everything, now we manage the orchestration for you. So we realized like, hey, this was way early in the space when Kubernetes was not really a big thing in the industry. But we realized that customers like the orchestration, but then customers are not familiar with Kubernetes. So we were like, okay, now how do we take a step forward where we kind of like give you the benefit of both the options? That's where we ended up starting with Elastic Cloud Hosted, which is our cloud product, where we orchestrate the infrastructure and we kind of like give customers the control of what they need to do. So that's where we started entering into the world of simplicity. But then there was still a lot of things that customers need to manage. So we'll get to a next slide where we talk about that customers still needed to manage their own clusters. They still needed to manage the capacity of how they want to size up their cluster. So there's still a lot of manual work that customers need to do. Now, with our latest product that we recently launched, it's called Elastic Cloud Serverless, where we manage everything. So now customers only need to care about building their own applications. They don't need to care about the infrastructure. They don't need to care about should I plan for capacity. They don't need to care about how would I scale up and scale down. Everything is much more automated, right? But at the same time, with serverless, now we want to give customers a great out of the box experience, which means you don't have the ability to control each and every setting. So people who are familiar with kind of like playing around with the nuts and bolts, now we have kind of like taken it down where we are making some things more opaque, especially on the infrastructure side, while giving the same set of flexibility on the application side. So with that, this is a very quick hosted overview of what the product has been. So we have been operating this product for more than 8 years, where some people even call it like Elasticsearch as a service, but it's way beyond Elasticsearch. To give you the kind of scale, we have tens of thousands of deployments running on this platform. In terms of containers, we have close to like 600,000 plus containers, which we run on a homegrown solution. So this solution was built even before Kubernetes was a thing, right? So everything is kind of like a custom-based homegrown solution. We operate 58 regions, which are spread across 3 cloud providers, and the 3 cloud providers are AWS, Azure, and GCP. So we offer a breadth of regions globally to our customers to choose from. And our platform sees almost petabytes of data ingested daily across the customer base, right? So that shows you how big our platform has been able to do so. And the fun part is that all the features that we offer to our customers work the same seamless way, irrespective of the cloud provider. So that's our goal, where we abstract everything and do all the fun stuff or the hard stuff for the customers. So customers only see that, hey, I just need to choose a cloud provider and a region, and all the features that they use are consistently working across the platform. So when we started to think about serverless, we knew that this is the scale that we want to initially start planning for, because we have a goal that at some point of time, serverless would be the best product ever that we have built, and kind of like reimagining how we build our Elastic product if we were building it right now in 2025, right? Which means the initial scale was set up, which is a daunting scale. But we also know that in the future, when we are building the serverless product, we are not building for the current state, we are building for the future state, right? So we at least had some boundaries, but then obviously the question comes up, like, why are we building serverless? And this question, you would see a lot of different variations across the board. If you go and talk with people from, let's say, the engineering side, they're like, hey, maybe we have a lot of tech debt that we have created. Maybe we are not moving fast enough, right? If you go and talk to people on the business side, they're like, hey, maybe we can charge people more money or we can improve our margin. If you go and talk to people with sales, they're like, hey, customers are totally frustrated with managing everything, right? So you hear bunch of different variations of what customers kind of like care about. But I think the main key item is that the customer expectations have changed over the years, which means now customers only want to care about the use case. They don't want to care about how they size it, how they monitor it, and how they maintain Elastic. So if you look at the slide, which has a graph or kind of like image on the right side, you can see that this layer of operations, which is highlighted, which includes kind of like maintaining the cluster, sizing the cluster, and kind of like having a backup restore option. This is currently in the hands of customer in hosted. With serverless, we take that whole bucket and move it in the management of Elastic, which means customers only need to care about the data and they only need to care about configuring the security controls. That's it. They don't need to care about infrastructure. They don't need to care about orchestration. They don't need to care about how would I manage my system. They don't need to care about like, hey, I have a Black Friday, Cyber Monday coming, and I need to scale up by 100x. Everything is done automatically by the system where we take off, right? So that's one big thing where customers want to reduce their operational burden. So that's kind of a common theme that we have been observing. And one more interesting thing that we have been observing is with like customers want to pay only based on usage. They don't want to pay based on provision capacity, right? So we always hear that, hey, I'm only using for 8 hours a day or 12 hours, or it's a spiky workload. I don't want to pay for the whole time, right? So those are some of the reasons on why we did think about serverless, because we wanted to be customer first, right? And that's where everything else comes later on in terms of the overall customer journey. So to give you a quick overview of how we try to think about at a logical layer. So Elastic Cloud is the parent hierarchy, which you see the first part. Then customers can create an organization. So you can have multiple organizations which a customer can create, or they can even have a single organization. And within an organization, customers has the ability to choose either hosted or serverless, right? So in hosted, we offer kind of like the same three solutions which you see on the serverless, but on hosted, everything is in the single deployment. So you can create a deployment and you can use either of Elasticsearch, observability, or security, right? On serverless, we broke that silos down because we realized that customers who use observability products to kind of like monitor their applications, they don't care about the security features, right? Vice versa, what we realized that customers who are developer focused, who really need to just put up a search bar on their website, they don't care about all the observability and security features, right? So that's why we created a more user-centric workload so that customers can get the appropriate set of things that they need, right? But the goal of this whole structure has been to treat serverless at the same level as hosted, which means all the benefits that customers get from hosted and all the features that they get, we have to ensure that customers also get all of those primitives in serverless over time as well. So with that, this is where the meaty topic starts into the place, where you can kind of like look at the architecture of both our products. So we will go into each segment of what is shown on this architecture, but I just wanted to bring this a quick slide so that you can look at the first image, which talks about the existing architecture of Elastic Cloud Hosted. And just by looking at image without even reading any terms, you can see like there are so many boxes and it seems to be a lot bloated when you look at the below picture, right? Which means that there's a lot of complication that happens in that image and the architecture, right? Which means there are a lot of layers where customers have to take a bunch of decisions and they have to manage a bunch of things, right? Whereas if you look at the new architecture of Elastic Cloud Serverless, you see there are no kind of like dangling arrows. It's much more linear and much more straightforward. You also see that there are much less boxes in general on that architecture, right? Which means everything is much more simplified, right? So we will talk about more about each component, but always keep this in mind, like our goal was to make things simple with serverless. So this architecture at least gives a starting point of how we are able to achieve the end goal. And now we would start with each of the particular segment. One thing to keep in mind is on the existing architecture, you see a big box on the top side, which kind of like shows the pattern. So in this, how customers use the product is like they are ingest clients. So you have agents, you have beats, you have Logstash, where you kind of like put the data into the Elastic segment, Elastic cluster. And then there are a bunch of things that happen. So you have a hot tier, which is kind of like similar to like, hey, you need fastest results in milliseconds and you are like latency very sensitive to it. So you need the best performance, right? But then obviously there are multiple different layers to that because not all customers want to store the same amount of data and get the same amount of performance, right? You might have a use case where you want to store years of data just for archival purpose or just for compliance purpose, but you don't query it enough, right? So we kind of like created multiple tiers so that you can kind of like manage and control how you want to move your data and how you want to shift your data, right? However, one big challenge with this architecture is that the compute and storage are co-located with each other, which means that we have the storage which is directly with attached to the compute. Now think about a scenario that your compute goes down. Now what happens? How do you get your storage because your data is being ingested every millisecond or you're querying the data? How do you ensure that your compute node does not take away all the storage, right? That's where we kind of like call this term more of a stateful term, where you kind of like have the compute and storage co-located. And that was one of the big things that we realized that with serverless, we want to move away from a stateful world, right? The initial interpretation of someone who was thinking about serverless was like, hey, we have a hosted product. Let's add autoscalers everywhere on every tier, and let's call it a serverless because some people also call those products as serverless. But then we realized that we have a big problem with the state being persisted and saved on the storage, right? So that brings us to the first design consideration on how should we think about building a product, right? So you have this question of stateless versus stateful. And when we kind of like realized from customers were always kind of like really challenged by, hey, Elastic, you are storing the state, which means that if something goes down, we have to manage the state, right? And this has been a constant challenge for Elastic in general because it complicates our operations because we don't want customers to lose their data, right? So as we build our homegrown operations and solution, we have done a bunch of things just to manage this operational part, right? Which means that we have built out a lot of kind of like small workflows so that we don't impact the customer experience when the node goes down. And as you know, operating a cloud service, node can easily go down at any given point of time. Sometimes the cloud provider does not even give you a notice. They just take away the node and say like, sorry, we took away the node for you, right? So we have been really investing into this operational aspect. And obviously, there's also a part of customer responsibility where we say customers, you have to build in the service and operate it with multiple AZs so that you have fault tolerance. And then we have advanced backup and restore mechanisms so that if something goes wrong, even in all the AZs all at the same time, you still have the data backed up in the object store, right? However, we realized like this is not a good way. And the initial interpretation of someone said, let's put auto scaling over there. We realized that the data would not be kind of like persisted and we need to figure out a better solution, right? That's why we ended up kind of like looking at a stateless ecosystem where can we offload the data from compute? Or even better, can we store the data not in compute, but use compute as kind of like a cache layer, right? That's where we started to think about like, hey, where can we put the data so that the data becomes a source of truth, right? Uh, we started to think about like, hey, how could we decouple the index and search, right? So in the previous architecture that we were talking, you have the ingest and the query also hits the same kind of tier, right? So how do we decouple? How do we ensure that customers can scale the index tier and the search tier very differently, right? And when we started to think about all of these, we realized that we can only do this when we re-architect the whole Elasticsearch product. So building out a stateless architecture touched each and every single line of the code that went into Elasticsearch for the last 10 years. And we rewrote most of those components to be able to remove the possibility of saving state directly on the compute, which means we had to take much more trade-off decisions that we'll talk next, right? Which comes down to like, okay, we took the decision to make stateless, but where do we store the data, right? What are the considerations that we need to take, right? So initially, when we started off with Elastic Cloud Hosted, our initial approach was like we would just store the data on the local NVMe SSDs, or we would just attach managed disk, which is like EBS volumes, and just attach it with the compute, right? Over time, we realized the operations and the pain it brings in, right? And then we also started to realize that as the amount of data is growing, because in the last 10 years, the explosion of data is happening with you too. Everyone wants to make sense of the big data that they have. We realized that we cannot offer customers the same set of performance because it becomes too expensive for customers to manage that, right? So that's why we kind of like optimize for search. And we introduced a concept which we call searchable snapshots, where you can search directly the data from object store, right? So we started to already think about primitives on how can we store the data directly in object store or directly away from the compute, right? And that was kind of like the formation for us because we realized like that's the path where we could achieve kind of like putting all of the customer data in object store. But then we were not sure because at the scale that we were talking about of ingesting petabytes of data, we wanted to get more guarantees that can object store handle it, not in terms of storing the data, but in terms of retrieving the data fast enough for us to kind of like play around with that, right? So that's why we did bunch of POCs over the few months to actually see could we be able to build out a stateless architecture that takes object store as the primary data store, and we realized that it seems to work, right? And this is all before we even put up a single line of code. So this was more of like how can we predict and how can we be more confident so that we kind of like move fast over there. So how did we ended up with Elasticsearch Serverless is like we use object store as the primary data store. So all the customer data, which is kind of like indexed and all the metadata is kind of like stored directly on object store, right? Which means object store is the source of truth, right? Now it improves and brings in a lot of benefit because you don't need to replicate the data. So previously for fault tolerance, you were saying customers replicate your data to two AZs. Now they don't need to do it explicitly because we can take advantage of the benefits and kind of like the nines that the object store provides, right? Now we have lower infrastructure because we don't need to bring in all the data and store it on the compute, right? Which benefits the customers directly. And we do also have higher durability, right? At the same time, for the search process, we were kind of like already taking advantage of searchable snapshots. So we kind of like doubled down on that. And we kind of like started to use that where we would persist the data in object store, but then we would pull in the data so that we can have the cache data in the local store or the managed disk, which means that the data that customers need is very closely located to the actual infrastructure that they're operating on, which means that they would still get the benefits of the fast results of the hot tier without sacrificing and storing all the amount of data, right? So this is where you can see that there are multiple layers to your architecture where you have to consistently think on where do we need to pull in the right set of ecosystem and architecture so that you don't end up just creating a product which does not help the customer in one way or the other. And obviously, kind of like the customer experience is kind of like top of the game to build that way, right? So now we talked about the stateful versus stateless. Now we talked about the data store. The next is like, okay, we know that now how do we put in, yeah, sorry, go ahead.
On the previous
Yeah.
slide, there has to be a latency issue if you're doing snapshots because you haven't had time to fully integrate. So it's eventual consistency. So how do you control that latency issue?
Yeah, that's a great question. So are you talking about the latency issue in a hosted or with serverless?
The first one, well, any of them.
Yeah.
So when you have a searchable snapshot, you haven't integrated your index yet. So there's basically a recent index sitting there that you can query into. But what if they need to query the whole thing? How long before eventual consistency sorts out?
Yeah, that's a great question, right? So when we introduced the searchable snapshots on hosted, that was primarily for the data archival use case, which means customers want to store the data and they want to query at some point of time or never want to query,
So
right?
it was colder data.
It was kind of like the colder data or the frozen data or the data which is less frequently accessed, right? So in that case, latency is not an issue. But you bring up the really good point on how do we solve the latency issue with serverless. And that's where it's like, we are kind of like, we looked at the customer experience, right? And we realized that when customers ingest the data and when they try to search the data, there is kind of like a distribution where you would have a small set of customers who retrieve the data at the same time as they're ingesting. And then you would have the average set of customers who can wait for maybe a second, 2 seconds, 5 seconds, or 10 seconds, right? Based on that data, we were kind of like looking at like, okay, if we don't have to provide near real time, we can maybe provide a delay where we store the data, cache the data ASAP. And then we also started to realize that why not just store the data directly on the cache first and then also kind of like replicate the data on the object store, right? So we ended up with playing around with both the options and we realized that we could first store the data on object store, cache the data. There would be a delay of few seconds. And based on the data and the customer research, we think that it's still good enough for customers not to be worried about the data need to be near real time. But that's one of the constant things that we would also talk at the end, that this is just the start of the journey, which means there are many more things and questions that we need to figure out over time as well.
Okay,
Does that answer your question?
yeah,
Okay.
thank you.
Sounds good. So now as we talked about, we need some compute, we need some storage. Now, how do you actually use the compute, right? So going back to our hosted world, if you realize that we already have a homegrown solution, which we call kind of ECE, on which the Elastic Cloud product is built, which kind of like does the same set of container orchestrations that what a Kubernetes provide, right? But this was just built before Kubernetes was even a big thing in the market, right? So there was a really interesting statement which all sparked this conversation, and that's in the headline. And someone said that we are spending too much human capital on just the container lifecycle management, right? Which means that are we doing the right set of things? And is it really required for us to spend so much amount of time having actual humans work on things that to manage the whole ecosystem? As we started to unpack the layer, we realized that we are not the only company who needs a solution like that. So we are not unique, right? Which means a lot of customers who are running orchestrators in food and containers, they need a good orchestration mechanism so that they can take advantage and invest into that, right? Uh, we then also realized that what we are spending time on our homegrown solution, we're not adding any value to our customers because customers don't care about all the operations that we do. Customers care about the features that we provide to them and how we make the quality of life much more easier for them, right? Which means we were taking all of this precious time away in managing the ecosystem rather than building and adding the value to the customers, right? At the same time, we also realized that uh, Kubernetes has come a really long way, which means that the pace at which Kubernetes has kind of like expanded, it has been much more faster. You have a lot of people who are maintaining the product, you have a lot of people who are contributing to the product, and it has gained a global adoption, right? And that begged our question of like, could we save human capital if we invest into Kubernetes, right? And at that same point of time, we were like thinking, okay, if we have to even build something on Kubernetes, why would we want to build it? And that's where we kind of like set a very clear and simple goal that we want to build around Kubernetes so that we can achieve a lower TCO for our cloud product by having economies of scale, faster iteration time so that we can build products and things much more faster. We have less operational overhead, so we don't have to do a bunch of homegrown things that we have done. And at the same time, we future proof ourselves so that we can keep on adding more building blocks over time as well, right? So thinking about this journey, this was the goal that we all realized that, yeah, this seems possible because everyone else in the industry kind of like towards Kubernetes to provide a similar set of benefits. And that's where we realized that this is something that we need to evolve and start looking into a little bit more closely, right? So for us, we wanted to embrace Kubernetes as an orchestration so that we can focus actually on innovation rather than just doing a container management, which does not provide direct value to our customers. So, so having said that, now the question is that, okay, what flavor of Kubernetes do you want to use? Like you have a CSP managed Kubernetes, you can also download the Kubernetes and do a self-managed Kubernetes, right? For us, this question, which is really complex in general, was very simple because none of our infrastructure teams had any idea about Kubernetes. So we were starting from zero, where no one in the company knew how Kubernetes work, right? And at the same time, we had took an ambitious goal that we want to build this Elastic Cloud Serverless product from scratch in 1 year, right? Which meant that the only way for us to do that was if we don't think about how do we manage the Kubernetes layer, but rather just start quickly enough by using a CSP managed Kubernetes so that we can start with faster iteration and we can deliver faster with lower operational overhead, right? So that was something that we quickly realized that we cannot start with the self-managed Kubernetes, right? But at the same time, if you recall, we wanted to build a Kubernetes product that works across the 3 cloud providers, right? Which means that you now have to start look into that, hey, what if AWS provides a Kubernetes offering? Would we get the same benefit on Azure or GCP, right? And then you start entering into what are we trying to optimize for, right? So this table kind of like gives a quick overview on some of the factors. which kind of like talks about what are the benefits of using a CSP managed Kubernetes versus what are the downsides of that, right? So for example, you can look at standardization. Like it's very easy to standardize a Kubernetes environment or a setup within a particular CSP, but it's really difficult to maintain the same set of standardization across all the three cloud providers, especially because the Kubernetes product that each cloud provider provides is not the same. It offers different set of functionalities and different set of aspects, right? Another key point for us was provisioning. Like how do we provision this Kubernetes cluster, right? And when we start think about a single CSP, every CSP makes it very simple to start because they have the CSP native tools, right? But then it means you have to interact with multiple different CSPs because every CSP has a different API, right? Now you start ending up in this world like, okay, I need to use 10 different APIs on AWS, but to make the same thing work on GCP, I need to use 10 more. On Azure, I need to use 10 more, which means now there are a lot of, at a layman level, a lot of if and else in the code where you're like, if AWS do this, if GCP do that, if Azure do that, right? So you start realizing that there are benefits of a CSP managed Kubernetes, but then you can't control everything. And that goes back to the control and simplicity slide that we had earlier seen, right? So we realized, we identified there are some factors where we would be challenged, but then this was the only way where we could iterate faster with lower operational overhead, right? So with that, now the question came in that how do we manage the Kubernetes provisioning layer? So as I talked about different APIs, different CSPs, now how do we do it and make it easier for our engineering team and our service teams to build the workloads and the applications over there? So before we even thought about what provisioning layer, where we have four options outlined in this table, we had thought about what our requirements were in a very simple and a high level term. And our requirements was that we need the ability to provision and manage the Kubernetes clusters across the CSP, right? But we wanted to do it in a cloud agnostic API way so that we don't end up with multiple different APIs that each engineer needs to care about. Rather, we wanted to build a platform where for any engineering or service team that works at Elastic, they hit the API. API itself knows whether what API do it needs to hit on AWS, Azure versus GCP. So we were looking at a cloud agnostic API platform layer for that to happen, so that we can make our operations really simple. And we wanted to do it in a cost efficient, right? So when we started to look through those requirements, the four set of tools that came into our mind as we were kind of researching, one was Crossplane, one was CDK Terraform, which is kind of like a version where it's all Terraform based, which is an infrastructure as a code. The third one was Cluster API, which is a really famous Kubernetes abstraction and a provisioning layer, which kind of like works really well if you need to manage the Kubernetes clusters. And the last one is Anthos, which is one of the GCP products where they allow you to manage your deployments across all the cloud providers, right? So whenever we started to look at the options, we always went back to our requirements. And that's where you can see that for us, multi-cloud support was really important. So we wanted to pick up a tool which has a multi-cloud support. That's where Cluster API kind of like did not cut the bill for us because it did not have enough coverage and we did not have a good confidence and a sense of where they are moving towards, right? So that's why Cluster API was not a good fit for us. We wanted to have the infrastructure actually abstracted from the engineer and the service loading team. That's why the CDK Terraform was not a good fit for us because there was no built-in abstraction. And we realized that if we have to build in the abstraction, we would actually end up building up an abstraction there on top of Terraform, which was exactly what Crossplane used to provide. So that's where we realized that CDK Terraform may not be a good fit for us. Now, going back to the last requirement, which was cost efficient, we realized Anthos meets the technical bar, but it's just way too expensive. Like if you do a magnitude of comparison, Anthos would be way expensive once you start hitting a particular scale, right? And that's where we realized that it would become too expensive given we knew what our initial scale was, which was the Elastic Cloud hosted, right? So taking all of those things into account and also taking into account that we are an open source company because we started with that, Crossplane is an open source product. So we kind of like had a huge bias towards that initially, but then when we created this table, it made life much more simpler for everyone to understand. And in addition, we have contributed a bunch of features to improve the cross-plane product, because not a lot of companies are using cross-plane to build Kubernetes across the 3 cloud providers. So we are able to improve the open source product as well as taking advantage of how do we kind of like build abstraction on top of it. Go ahead.
Did you look at Azure Arc at all?
Yeah, Azure Arc was not there when we started off, and when we did look at it, looked very similar to Anthos. And with Azure Arc, one more interesting thing was that you are bounded by the scaling limits of what Azure Arc has on each of the cloud providers, which means if you want to scale like unnecessarily to an abstract number which is high enough, you have to go and tell Azure like, hey, increase the scale limits. And that was another challenge we had with Anthos, where they only had limits based on what they have tested. And we knew that we wanted maybe a much higher number that they did not have confidence to kind of like provide us.
Capacity limitations.
Yeah, capacity, quota limits. It's more of like how would thousands of nodes work on a different cloud provider where the control plane is not there.
How about Spectro Cloud?
We did not look at Spectrum Cloud. So moving forward, so now we covered how we would use the Kubernetes. We use CSP managed. We realized we need an abstraction which was cross-plane. Now, how about the network interface, right? So I would be very transparent. I'm not an expert on network interface, right? But what we do care that first, whatever we choose as a product, that should work across the cloud providers, because that's a very simple primitive that we're trying to build. We want to ensure that all cloud providers actually support it in a native fashion, right? We want to ensure that as our use cases are driven by customers, which is very index heavy, we want low latency, right? We want high performance so that the Kubernetes clusters can scale up with minimal network overhead. And we wanted one more very specific requirement that the CNI should actually be able to build tools on the L7 layer on the OSI protocol, which means that it needs to be application aware, which means that we can build rules based on the application, right? When we looked at a bunch of tools, which I didn't have on this slide because the list of tools that we saw were like much bigger than the previous slide, we eventually chose Cilium because that's kind of like a product that's coming up, which kind of like meets all the requirements. And I think there was one more tool which met the requirements. I forgot the name of what that was. But within both of those tools, we realized Cilium is a much better choice because it supports policies at the L7 layer, whereas the other tool only supported policies at the L4 layer, which means you can only add logic based on the routing. You cannot add application specific aware logic over there, right? So when we initially chose Cilium, our initial plan was like, hey, we would implement a self-managed Cilium across all the cloud providers because we wanted to standardize our offering, right? We then realized that every CSP has so much variation on how you can self-deploy the Cilium that it made the uniform approach much more difficult, right? And then how we ended up was like we would look at which CSPs provide us a native Cilium. So GCP and Azure has a native Cilium product, but AWS does not have a native Cilium product. So we ended up with using managed product on GCP and Azure and the self-managed Cilium on AWS, right? But the catch is now you have different CNI configurations, different set of functionalities that each of the cloud providers provide. So we ended up leveraging the common set of features so that we kind of like cover our bases, but at the same time, we know that we are not utilizing the managed Ciliums at the right set of scale because we could do a lot more. But if we do, then it would be CSP specific, and we don't want to build some CSP specific rules, right? So, so we talked about a bunch of containers. We talked about the compute and the infrastructure. Now the question comes into the control plane and data plane. So for those who are not fully aware of how we kind of like define those terms, I have some definitions. At a very high level, control plane is the layer which manages all the management that the customers does, right? So if you need to kind of like manage your project, or if you need to create a project, you would send out a request that goes to the control plane. Data plane is the layer where your actual data gets stored on the Elasticsearch side, right? So if you want, like that's a whole infrastructure there, which kind of like works so that they can power your particular Elastic Cloud Serverless project, right? So now you can see that having two set of layers, how would these layers interact with each other? Because when a customer requests something, they would hit the control plane. But then when they're actually indexing the data or querying the data, they need to connect and communicate with kind of like the data plane, right? So that's where we ended up with the next conundrum that we had is like, what model should we should we use for the data plane? Should we use a push model or a pull model, right? I know the push and pull is very difficult to understand. So that's why I put in an example, right? Like, hey, when a new project is created by a customer, the global control plane needs to communicate with the Kubernetes control plane in the data plane because they need to know and tell each other that, hey, I got a request, now you need to do something to manage that request, right? And in those terms, what would push me is that the global control plane, they would push some configuration to a particular data plane cluster, right? Whereas what would happen in a pull is that the Kubernetes clusters in the data plane, they would continuously watch and they would need to pull the configuration from the global control plane, right? So that's where you end up with an interesting question like, hey, do we really care about push versus pull and what model should we choose, right? We eventually chose push because of multiple reasons. One of the reasons was that we wanted a very simple scheduling logic where we have a global control plane, we send out a request, we know global control plane would send out and say like, schedule this pod on a particular Kubernetes cluster, right? So we wanted the global control plane to actually choose the actual Kubernetes cluster on the data plane, right? So for us, that simplicity was really important, right? With the push, you would realize that there's a one-way communication which is happening from the global control plane to the actual data plane. But in pull, you can realize that you would have a bidirectional communication because the data plane would keep on communicating with the global control plane to realize if there are any changes or not, right? So that's a much bigger complexity that is introduced in the pull model, right? Also, what we wanted to do was that if by any chance we have a failure where the actual global control plane goes down, we did not wanted our data plane to suffer, right? So in the pull model, let's take this scenario. The global control plane goes down. The data plane is trying to pull for changes and it requires, and now it receives no heartbeat. Now the data plane does not know what the hell it needs to do because it cannot monitor for changes, right? And that puts it in a very difficult position of how do we handle that particular logic versus in the push model, if the data plane kind of like if the global control plane goes down, then there is no communication happening, but the data plane is still operating. And obviously, you don't want a direct customer impact. That's where you can do some manual or semi-automated stuff, where even with the global control plane going down, you don't at least allow the whole application to kind of suffer, right? So for us, that was more important that how do we start with something simple and how do we ensure that we have failover scenarios created just in case the whole application does not die if one thing does not work. And obviously, as one of the famous saying is that something would eventually fail at some point of time. So however great any of the product in this world is, every product fails at some given point of time. So kind of like quickly, kind of like moving upwards, right? So we talked about compute, we talked about the networking layer, we talked about a bunch of aspects of the layers. Now the big question comes up to an auto scaling because how do you scale your applications up? Because now we need to do it on behalf of the customers, right? And if you start realizing auto scaling, you would start realizing like, hey, it's such a simple thing. Just scale up based on memory, scale up based on CPU, right? Scale down when it's not in use, right? But then you also start realizing that those are not the only dimensions that could be impacted when you are controlling the whole management layer, which means we wanted to build out a solution where we have full control on what metrics we are choosing for auto scaling to optimize the scaling decisions, right? And obviously over time, we evaluated multiple different options, right? So there is a horizontal pod autoscaler. What it does is horizontally scale up so that you don't have to, like, it creates more nodes to scale you up. Then at the same time, you have a vertical pod autoscaler where you scale up from a smaller size to a bigger size, but keeping the same machine, right? Then you have a cluster autoscaler, which does a combination of the both, right? Initially, we wanted a very simple approach. So we just started with the horizontal scaling where we would add nodes. If we need to scale up, we would add more nodes over time, right? But we realized that as we are running bunch of services, not all services want to scale horizontally. Some services want to scale based on CPU and some services want to scale based on only memory, right? So we wanted a trade-off, right? We realized that as there would be a lot of services that would be built on that platform does not need to take any decision for the service owner because we don't know what the service needs to do, which means we wanted as a platform to support all type of primitives. So we ended up kind of like building our custom auto scaling controller where we can now actually specify the metrics based on each application and workload on how they want to scale, right? So for example, you want to have a different heuristic on how you want to scale the indexing tier, which is more around the CPU utilization, or kind of like the amount of data you are kind of like ingesting and the frequency of the data. Whereas in the search tier, you want to query on very different dimensions so that you can take advantage of maybe the heap memory, right? You can take advantage of how much of the actual cache size is being used, right? So you start realizing that for each of those tiers, you need different set of heuristics and metrics to actually auto scale, right? And we also wanted with custom auto scaling, what we also get is that we can make intelligent scaling decisions based on each of the workloads. So even in indexing, you can have multiple different service running on top of the indexing tier. You don't want a same set of solution that works for all of those services, right? So for us, what custom auto scaling actually provides that it helps us to iteratively enhance auto scaling because now we enable each of the service to think about whether they need to scale horizontally, whether they need to scale vertically, whether they need to scale a combination of both. But we give the direct control in hands of the actual service owner so that the platform does not need to get involved in what kind of scaling strategy that the service needs. So this is a powerful kind of outcome because when you start realizing that you don't have a one size fit all approach, you don't want to end up kind of like being in a position that every service tries to come to you, say like, hey, we need something specific, right? That's why thinking about it and building it in the main architecture and the platform just makes the life super easy for service owners over time. Last but not the least, all of that was more of a technical decision, but what is in there for the customers, right? And for customers, it was all about a big part of it was pricing model, right? And when we started to think about pricing models, we were like, okay, what should be our goal, right? Going back to the definition of serverless, a serverless product has very different set of pricing models in the industry, right? So for us, the goals were like, hey, we need to keep pricing simple, right? It's such an easy goal, but it's so difficult to implement, right? So we wanted to keep it top of the goal that, hey, we want to actually provide a true pay-per-use pricing model. So it's like if you use, you pay. If you don't use, you don't pay, right? We wanted to minimize the initial pricing dimensions because if you go and look at some of the industry competitors in general, you would get confused because they have tens and hundreds of pricing dimensions to even figure out how would you price it, right? So we wanted to start off with very simple set of dimensions so that we can keep on improving and iterating over time, right? We wanted to incentivize customers to use the AI and ML capabilities, right? That's why some of the pricing model that we ended up choosing would help customers to kind of like take advantage of those capabilities in all shape and form, right? And last but not the least, we wanted to incentivize customers to actually use the product continuously over time. So going back to the pay-per-use model, if you have set of customers who are using only for a few hours, then you have to keep the infrastructure in one way or the other, right? So you kind of like incur the cost. One way of passing that cost to the customer is high price, right? But we don't want to do that. That's why our pricing model wanted to kind of like incentivize customers to use the product more and more over time, right? So in our journey, we looked at all the options that in this world exist for serverless, right? We found these 5 categories of how each of the competitor and the industry product thinks, right? So some price it based on the read and write operation, right? Some price it based on the amount of data scanned. Some price it based on the data ingested and data retained. Some companies even have a minimum workload unit consideration, which means irrespective of the usage, you would always have a fixed baseline cost, right? And when you question them, hey, serverless is truly pay per use, they're like, yeah, we have our own definition of serverless, right? So we realized that there are a bunch of different options that we can go off with, but we went back to the drawing board to actually see that what our customers would want to use, right? That's why we ended up like, we have three solutions: observability, security, and search. But each of those use cases vary so differently that we cannot offer a single pricing model, right? That's why we realized that observability and security are more kind of like ingest the data and make sense of the data, which should be more coupled together. That's where we ended up kind of like pricing in a way that we price it by data ingested and we price it with data retained, right? Now, going back to our goals, right? We wanted customers to take advantage of ML capabilities. Now we don't charge anything extra for customers to enable ML. That's all built in the particular pricing model, right? We wanted to incentivize customers to use the product continuously. So we introduced tiered pricing. The more you use, the more cheaper it becomes for you in terms of pricing, right? Which means customers can now bring in a lot more amount of data, and each dollar of data that you bring in is much more cheaper for you than the first dollar or first gigabyte of data that you brought in, right? For Elasticsearch, we realized that there are different workload units that we need to create, right? That's why we ended up creating ingest, search, ML, and data retained, right? Now, obviously, you would question, why do we have ML over here in search versus why don't we have it on observability and security? And the main reason is that you can use ML in a very different capabilities for the search workloads, where you can do start from anomaly detection. You can go as advanced as vector search and kind of like storing the embeddings and vectors inside Elasticsearch. So due to the breadth of complexity, we did not want to kind of like provide a pricing which would be cheaper for some and expensive for others, right? So we wanted to be a bit more transparent, right? In addition to these, we kind of like priced it out in a way that we only charge for data out. So whatever data you're sending outside of Elastic, maybe to some application which is running in some other workload, some other cloud providers, and we introduced a bunch of add-ons so that if you really need to care about some other functionalities, but not all customers do care about it, right? So that should be an incremental cost if you want to use it, right? And last but not the least, what it means that we don't charge if the usage is idle, which means customers actually only pay for the amount of data that they use, right? So kind of like just summarizing all of those, but before we do that, we can't talk about cloud without talking about capacity, right? And when you talk about a capacity problem, you are like, hey, what the hell you are talking about? Cloud has unlimited capacity, right? But then you end up with an out of capacity error. So you go to CSP and CSP says like, hey, we don't have that problem. And we say like, hey, we saw the problem. So they're like, oh, sorry, you got a problem. It will take some time, right? And when we ask how much time, we wait forever to get the capacity because there is no SLA provided by any cloud provider on how quickly you would get the capacity, right? Which means that you have to wait forever. And we learned it really hard way. So when we build out our cloud hosted product, we allow customers to choose a hardware profile, which is backed by a particular instance type, which means if that instance type is out of capacity, customers cannot scale up. New customers cannot use it, right? So we realized cloud is not unlimited. It's a false promise. So if anyone says that to you, run away from that room because it would never be true, right? But what we wanted to do is that we wanted to move away from that inflexibility to a flexibility world, right? That's where what we ended up putting our goals was that we always want our workloads to run on the best price performance instance type. But obviously, you cannot expect that instance type to be available always, right? That's why our secondary goal was that we want to allow workloads to run even if the preferred instance type is not available, right? And the goal that we want to achieve is we want to have zero out of capacity error for the customer so that we take away all that complexity of scaling up, managing scaling, managing for events. Everything is automated in a way that neither the customers need to worry, neither our engineering teams and operation team needs to worry, right? How we ended up doing that was we ended up with an outcome where we created priority-based capacity pools where we defined different priorities per workload, ensuring we always have fallback when we need, right? We have a failover strategy. So if the best instance type of P0 is out of capacity, we start running the workloads on P1. We start running the workloads on P2, right? And then we also do a lot of proactive capacity planning by using all the CSP native tools, but also working directly with the CSPs to ensure that we always are running the workloads on P0, because that's where the best price performance comes in for the customers, right? So if you have been with me for the whole session, don't worry about whatever I said. I kind of encapsulate everything in these main takeaways, right? The first takeaway is like building an infrastructure platform that provides similar functionality across the three major CSPs is challenging. Like we face that challenge when we build our homegrown orchestration on Hosted, but moving to the CSP managed products, it's much more challenging. You would always be balancing between reliability, scalability, and cost. You would always be trading off between, should I use this? Oh, it brings reliability, but then it does not bring scalability, or it makes the cost much more expensive, right? Kubernetes implementation is widely different across all three cloud providers, which means you would have different set of functionalities, you would have different set of maturity, and you would have a different set of reliability. So you would end up with maybe one cloud works really good and the other cloud works really bad, right? So you would end up with, how do we abstract that for our end customer so that they do get the same set of functionality, right? We also realized that when we are building a platform, we need to support as many functionalities as we can to make the life easy for everyone who is building on top of that platform, right? That's where we ended up with different auto scaling techniques. We ended up with priority-based capacity pools so that we don't end up disrupting any workload, right? And building a product is not just a technical challenge. It requires a mindset shift, because the way you operate, the way you build, the way your customers use the product is widely different, which means now we own end-to-end customer experience. So if there's any error a customer faces, it's Elastic problem to solve it for the customer proactively or reactively without the customer getting mad at Elastic, right? Which means we have to change the whole operation mindset. Now we own the whole operation, which means if there are set of errors that happen more frequently, now everyone would try to solve the root cause, figure out the root cause and solve the problem, because you don't want to have operations mindset very heavy on the engineering team, right? And we went from transforming ourselves from reactive troubleshooting way later after a customer actually report the problem to proactive optimization, where we now have a bunch of alerts at each customer project level, where now we actually know beforehand that this customer would end up in a problem, which means we can actually now start working into solving the problem even before the problem kind of like exists, right? So this is the main takeaway you should have it when you are building a product across the three cloud providers, that you need to do and be very diligent. And you always need to assume that things would not be the same. So you always have to struggle, but you should always go back to your requirements, goals, and outcomes to really push and figure out what's the right trade-off. And you would have a bunch of trade-offs all the time. So I know I'm over time, 5 minutes, so apologies for that. But I want to open the floor to see if anyone has any questions, other people who are with us virtually or people who are in this room. Go ahead.
So you said that you only have, like, you're trying to focus on the three major cloud providers. What are their share compared to the most users? So like, are they like 80% of cloud use, or are they like more like 75 or 65%?
So currently on Hosted, we only provide those three cloud providers, right? So it's like 100% of our user base, right? But then if you look at the industry kind of like readouts, you would see that AWS has the biggest market share. And when you combine the market share of the top three cloud providers, that's close to 70% of the market, right? So you have 30% of the market where you have operators like Oracle Cloud, you have operators like Tencent and Alibaba Cloud, which are much more bigger in the China space, because not everyone wants to have a China presence. You would have some cloud operators in the Russia space where you don't have ease of kind of like operating. So you would always end up with bunch of localized as well as global. But for us, our major customer base is based on the top three CSPs. So everyone is super quiet, which shouldn't be the case, because I have a bunch of questions when I'm presenting. So good. So if I can take 2 more minutes, I just want to walk through, like, this is just the start, right? We have a bunch of things that we need to figure out, right? For example, when we went towards what are the considerations for large clusters, we got this huge list of 20 set of items that, hey, you need to think about number of nodes, you need to think about the limit on number of pods, you need to think about how many disk that you can attach, you need to worry about how many IP addresses you're attaching, and the list never ends. And I got a really nice picture from somewhere on the web, which kind of like shows you a 3D image of like, hey, they are not one dimension, they are 10, 12, 15, 20, 30 dimensions, where you have to consider how you would scale your Kubernetes cluster, right? So it's a multi-dimensional thing that you need to consider, right? You would always need to trade off between customer experience versus the limits on Kubernetes, right? So you would always end up with scenarios like, hey, what if we only support X number of nodes or pods per cluster? But what if your existing customers scale up much faster and you exhaust the limit on that pods on that cluster, right? Or what if you exhaust some of the dimension out of the multi-dimension that we saw? How do you kind of like impact the experience, right? So we don't have solutions for all of these, but we are kind of like exploring some mechanisms where we can actually move projects across Kubernetes clusters so that if we kind of like hit any of the limits on a Kubernetes cluster, we don't impact the customer experience, right? So we kind of like want to build mechanisms to move projects without any customer downtime, right? You would always end up with, how do I even build out the set of priority pools for capacity? Because each, like when you think about capacity and instance type, you would always realize that a same instance type has different sizes. You would always realize that there are different instance types. So some are older, some are newer. You would always, and you would always realize that not all instance types provide the same configurations of storage, CPU, and memory, right? So you would always end up with like, hey, how do I choose the right instance type, right? Anecdotally, what we have seen is if a CSP is out of capacity for one instance type, then the smaller and bigger sizes of that instance type is actually also out of capacity, right? Which means you have to pick in your different priorities, which does not fall within the same boundary, right? If you have different families with different specifications, you would end up with less than 100% utilization of the underlying instances, which means your cost would balloon up if you're spending more workloads on P1 and P2, right? You would realize that not all instance types have the same storage mechanism. Like some have local SSD, some don't have local SSD, right? So you would end up figuring out how do we mix and match the different storage profiles, right? Then you also need to realize that your P0 is the best one, but if you're running P1 and P2, how do you move your projects back to the highest priority? Because that's where the customer gets the best experience, right? Object store cost adds up. So this is one of the really fun things that we realized, that the way a lot of companies and the CSPs charge you for object store, they charge you based on the API calls. They don't charge you based on how much data you are sending in each API call, right? Which means for our service and our workloads, if customer is kind of like ingesting data every millisecond, we have to make an object store call every millisecond to store the data, right? Which means that each cost quickly just adds up, right? And at the same time, going back to the latency question, one of the ways we could do that if we batch multiple requests and kind of like push the data in a single API call, but then that adds latency to the customer experience as well, right? So this is one thing that's very difficult to contain, because this is where the CSPs take away all the money from you. And that's where we have started to invest in kind of like identifying, are there any sources of API calls where we can reduce the calls without impacting the customer experience? Could we batch it? Could we do something more explicitly? Could we do something more intelligently, right? So all of these things, you would realize that there are a bunch of references that we have on our website that talks about most of these things in a one way or the other. But more interestingly, you would run into challenges. So that's the big takeaway, that you would always run into challenges, and it's not the smooth ride, but it's a ride that your customers would enjoy it because they don't need to worry about all of those aspects. So with that, I would try to end the presentation. Sorry, go ahead.
How about users that want to do extensions on your service? It's running on your cloud. Do you offer a way for them to plug in custom software?
So initially, we did allow customers to add plugins, right? We realized that customers can add any malicious code into the plugin, right? Because we don't have a plugin inventory management, which kind of like scans the code, does a bunch of things to realize if it's accurate or not, right? So we ended up with not supporting plugins. With serverless, we took that approach, but then we also have a concept called webhooks, right? Where we have integrations with like 400 plus data sources. So you can just quickly go select an integration, you can pull the data, push the data, so that you kind of like use a set of integrations rather than trying to just put some code which we don't know whether it's malicious or not.
You must have a lot of metrics as these are running. Are those metrics something the customer can pull into their own store, like Databricks or Snowflake or something?
Yeah, like with the webhook, like whatever data we expose, like there's a set of data that we expose directly to customers. There's a set of data that we keep it for our internal purpose
Okay.
for actually monitoring and optimizing the customer experience. For whatever we offer to the customers, they can just use a webhook and send the data to anywhere outside Elastic.
Do they use something like Kibana for visualization?
Yes, yes. A lot of customers use Kibana. A lot of customers who have already invested into building their own solutions, maybe on top of Grafana, Prometheus, or others, they want to use Elastic as a data store. So you would always end up with majority of the customers who are using or starting with Elastic, they would use Kibana. Others who already have invested, they would just want to use Elastic as a data store.
Do you allow customers to break their organization down so they can see if they have a resource hog inside their organization?
Yes.
So they can do that, they can break it up by account or.
Yeah, that's where I think one of the initial slide had an organization, and
Okay.
within organization, you can have your projects and deployments and services. And then you have admin controls where admin controls what they want to show. Then you have user permission where user sees and controls what they want to see.
Do you have capacity triggers? Because a user might have a runaway activity and that they don't want to just keep going infinitely.
Yeah, so on hosted, we don't have capacity trigger because it's in the customer's hand to actually manage that.
I mean,
It-
cloud.
Yeah,
Yeah.
in serverless, that's
Yeah.
our problem. So customers send us, let's say, 10 gigabyte of data. Whether we use 1 gigabyte of infrastructure or 100 gigabyte, customers don't care. We don't charge customers based on our infrastructure. We charge customers based on how much data they ingest.
No, I'm saying I'm the customer and I have 200 developers. One developer does something that causes a runaway, you know, and it's hitting me really hard. I'd want to know about that.
Yeah, so we have controls where you can add kind of like alerts that says like, hey, don't make my billing go away or go bigger than this. But then they are much more nuanced with serverless that we want to explore. So we are still in the early stages to explore more cost transparency or billing transparency controls.
When you connect to your data plane, to your control plane, what are you using there? Is it gRPC or REST APIs?
Yeah, those are set of APIs. I don't know exactly which protocol we are using, but it's more of like,
Use both actually.
yeah, so
It's what?
Use both, yeah.
we use both. We use the REST API and gRPC. So I have the expert who kind of like knows ins and outs about it.
Thank you.
Good. Any more questions?
Thank you, Yuvi. Thank you for coming. Thank you to you and thanks to Elastic. To come and give that great talk. Thank you.
Thank you.
So we have like probably 10 or 15 minutes. We can stay in here,
Yeah,
but then
thanks Julian for the laptop. You were not able to work for the last one.
that's fine. It's fine.
Better work out in the end.
Yeah. So how did you find the session like? I know there's a bunch of last in the world, but
Maybe you can
Oh.
leave.
you can just leave, sorry, I did not leave.
Oh, that's okay. You can just hit that. Hit that.